Hello, you're welcome back. All right, so we're going to continue from where we stop. Okay, we are still on electromagnetic induction, and here we're going to be looking at another device, okay, that actually employs the principle of electromagnetic induction, and that is a transformer. Okay, what's a transformer? A transformer is simply a device that step down or step up an alternating current EMF that is supplied to it. So basically, this is a diagram of a transformer, a schematic diagram, okay? It has two coils, the primary coil and the secondary coil, that is actually isolated but coupled, okay, in a, using a magnetic principle of magnetic flux linkage, okay? And they are being wound around an iron core. This is an ion core. So, of course, the primary core is so called. Why? Because that is where my input, where I supply the voltage. Then, of course, the secondary core is so called because that is where I take my output. All right. So it simply means that if I supply voltage at the primary core, then I will have an output. That output can be a step up voltage or a step down. Okay. So now, how does actually a transformer, how does it function? What is the principle behind the operation of a transformer? So that's what we're going to be looking at. Now, whenever I supply current, okay, at the primary core, definitely flux will be generated at that primary core. And the flux that is generated at the primary core is, okay, is proportional to the current that's supplied, that is being supplied. So let's this number of turns of the primary core, NP represent the number of turns of the primary core, okay? Then multiplied by the flux generated at the primary core. All right. So, of course, this is please pardon me, it's equal to not proportional. Okay. So the flux generated at the primary core is equal to the current that is supplied to the primary core. So now, of course, you know very well that if there's going to be a change in this current, if I have a change in current with respect to time, all right, if the current actually varies with respect to time, the same thing happens with the flux. The flux will also vary. The flux of the primary coil will vary with respect to time. The flux of the primary with respect to time. So please take note of that. Okay. And of course, we already know from Faraday's law that the flux, the varying of flux, the change in flux with respect to time multiplied by the number of turns is equal to the EMF. So that's going to be equal to, so what I have here now, change in flux with respect to time multiplied by the number of turns is going to be equal to the EMF induced at the primary coil. So the same thing happens if I'm dealing with the secondary coil. Let's say the current was actually supplied to the secondary coil, called secondary current, okay? Then of course, flux will be induced, will be generated at the secondary coil. All right. So if this particular flux varies with time, which of course it will vary with time because it's an alternating current. If the current varies with time, then of course the flux also linking that coil will also vary with time. And that varying of flux, secondary flux with time multiplied by the number of turns of secondary, okay, is equal to the EMF induced at the secondary coil. Okay. So now I have two equations, equation number one and of course equation number two. So I'm going to divide equation one by two. So I'm going to do, please pardon me, divide equation one by equation two. So let's divide that. Of course, I'm interested in this left hand side and right hand side, okay? The change in flux with respect to time. So let's actually flow with that. So I'm going to have NP multiplied by the change in flux of the primary Okay, the flux of the primary divided by delta T, then divided by Nx. Okay, then the flux generated at the secondary with respect to time. So it's equal to the EMF of the primary, that's the right hand side, EMF of the primary divided by the EMF of the secondary. So I already told you that the flux that is generated in any of this coil is being transferred because this transformer is being coupled. Okay, so the same amount of loss that is being generated at the primary would definitely be received by the secondary. Okay, and of course if that particular flux was generated at the secondary, it will equally be transferred, so it's equal. So the flux of both the primary and the flux, the change in flux of the primary with time and the change in flux of the secondary with time is always equal, so definitely they will cancel out. So I'm now left with NP, number of turns of the primary divided by the number of turns of the secondary, equal to EP, the EMF generated at the primary divided by the EMF of the secondary. So this is basically a transformer equation. Okay, so this is equation of a transformer. So from this equation now we can actually conclude that the number of turns of the coil, okay, actually is directly proportional to the EMF induced by the coil. So that means a transformer, if I have a transformer whose primary primary coil, okay, the number of turns of the primary coil is greater than the number of turns of the secondary, or please pardon me, is less than the number of turns of the secondary. Okay, we simply said that such transformer is actually step down. Why? Because the primary is, please, I'm using the secondary now, let me state it well. If I have a transformer whose output, which of course is the secondary number of turns, the number of turns of the secondary coil is actually greater than the input, the number of turns of the primary coil, then such transformer is called a step down. So such transformer is a step down. It says step up transformer. Step up. Pardon me, step up transformer. Why is it step up? Why? Because the number of turns of the secondary, which is the output, is greater than the number of turns of the primary. Okay, so it's stepping up the voltage. But a situation where the number of turns of the output, which of course is the secondary, is less than the number of turns of the primary, this is where you now have a step down transformer. Step down. Okay, so please take note of that. Now let's look at a typical example. Let's look at a typical example where a transformer is supplied with a primary voltage of 240 volts, and it happened that the number of turns of the primary coil is 2000 turns. 2000 turns. Then it is being coupled to a secondary having number of turns of 500 turns. 500 turns. So the question is, what is the EMF or the voltage of the secondary? So applying the formula, okay, NP all over NX equal to EP all over EX. So let's actually evaluate. NP is 2000 ton, NX is 500 equal to EP. EP is giving us 240 volts then of course divided by ES. So rearranging this, I have to cross multiply, okay? Of course, if I should divide this is gonna be 4. 2000 by 500, okay? That means that's 4. So if I cross multiply, I'm gonna have, if I cross multiply and of course rearrange to make ES the subject, I'm gonna have 240 all over 4, okay? So of course, 240 all over 4 gives me 60 volts. So while the input is 240 volt, the output is 60 volts, which shows that this transformer is a step down transformer. Step down transformer. Okay, so I hope that is well understood. So we proceed. Now we are going to be looking at some form of losses. Okay, losses that actually take place in a transformer that reduces the efficiency of a transformer. Now, you know very well that a transformer is supposed to actually transfer the flux from the input to the output. But, and of course, if that happens, by an ideally, a transformer is supposed to transfer all the flux, and a transformer is supposed to actually deliver a perfect output. But there are some certain losses in a transformer that will not actually cause that to happen, and that is what you're going to be looking at. One of the losses is losses that is found in the winding of the transformer. So winding losses. This winding losses is due to the resistance of the winding, because the the wire that is used for the core of the transformer is actually copper wire. Okay, and of course by the time you wind the copper wire, and definitely when you wind it, you're gonna have a very long, you need it's gonna be a long stretch wire, okay? And we know very well that in a wire, the losses in a wire actually in a conductor, okay, in form of a wire, actually comes in form of heat and is given by the formula I square R. I square is the current and R is the resistance. So which simply means that if I have a transformer that is supplied with a very high current, if the winding of that particular transformer is of a high resistance, then definitely heat will actually be produced. That particular transformer will produce too much heat, which will reduce its efficiency. Okay, so in that case now, for me to actually minimize the losses due to the winding of the transformer, I'm going to use a copper wire or any, okay, I'm going to use a copper wire that is very thick, because a thick copper wire will actually have less resistance. Okay, so I will need a thick copper wire. Okay, so what I mean by thick copper wire is a wire that has um, high cross-sectional area. So this is one loss you get in it, and that loss is loss due to what is known as AD current. Okay, now this AD current is actually induced in the core of the transformer, AD current in the core, because of course you know very well that the core of a transformer, okay, is metallic in nature. So of course that particular change in flux will definitely induce an opposing current in the core, that particular winding, the core that is used to transfer the flux, okay, and that can also produce heat. So now, how do you prevent that particular current, okay, that can be lost, that is induced in the core of the transformer that produces heat, known as eddy current? We do that by actually insulating the core of the transformer, the iron core, by laminating, okay? So you make it an insulator by laminating the iron core of the transformer. That is how we minimize such loss. Okay, then we also have another type of loss in a transformer known as hysteresis. Hysteresis. Hysteresis is a loss, okay, due to the changing flux. That's the speed of the change, the rate of change in flux, because the rate of change in the magnetic flux linking the two winding. Okay, now the ion core, that an ion core that have a hysteresis deficiency would not actually change, because definitely, in a transformer, the current that is actually supplied to the input is actually varying, and sometimes the variation can be, there are some current whose variation is of a very high frequency. Okay, for example, the alternating current that is being supplied, that you receive in your house, is of a frequency of 60 hertz. Okay, a very high frequency. So now, if this particular frequency as high as it is, we also can also have some frequency. This is, of course, is compared to some other higher frequency. Okay, like in radio transmission, you get up to a frequency of alternating currents whose frequency is up to 600 megahertz, very high. So that simply means that this high frequency of change in the flux, if that particular transformer is not designed, the core of the transformer is not designed to be able to handle this change, then definitely there's going to be losses. And that losses is known as hysteresis losses, okay? Due to the rate of change in flux. So if the core of the transformer doesn't actually changes as fast as the input signal, then definitely there's going to be losses. Okay, so basically, we still there are other losses, but basically these are the major losses in a transformer. Okay, so we are going to proceed now. We are going to be looking at the types of inductors. Okay, and we are going to consider two types. I'm going to look at mutual inductors and, of course, self-inductors. Mutual inductors, and of course, the inductors, or the electromagnetic induction that is actually used in a transformer, okay, that is used in the operation of a transformer, is basically mutual inductors. Why is it called mutual inductors? A mutual inductance is actually an inductance that is created in another coil due to the change that is happening in the coil that is close to it. And that is exactly what you see in a transformer. Okay, let me actually illustrate that. You have a coil and you have another coil. Okay, primary and secondary. Primary and secondary, very close to each other. All right. Now, okay, of course, it's coupled, but let me just forget about the ion cord for now. So this is the primary, and here is the secondary. Okay. Now, you discover that the variation, if the current supplied to the primary actually varies with time, the current of the primary varies with time, what happens? Actually induce, it will definitely induce, um, it will induce, please pardon me, it will induce a varying flux. It will induce a varying flux at the secondary. The change is actually taking place. The supply is actually, the changing current is being supplied to the primary. Okay, but you discover that changing supply, that current that is varying at the primary, now actually causes the flux linking the secondary coil to actually change with time. So that is what is known as mutual inductance. Okay, when and you know very well that of course, if I need to actually change this proportional sign to an equal, I have to introduce a constant, and that constant is what I'm going to introduce. That constant at the right hand side of the equation. Okay, so that constant is m, which I'm going to tell you what it is. Okay, that constant is what is known as mutual inductance. So so when I vary the current of the primary with respect to time, please pardon me, with respect to time, then definitely the secondary, we have its flaws. The flaws linking the secondary will actually vary with respect to time. All right. So now, for me now to change this proportional to an equal, I have to introduce a constant known as m. Now this m is a constant known as mutual inductance. Mutual inductance. So please take note of that. So invariably now, you know very well that from Faraday's law, the change in flux, okay, please, the N here is the number of turns of the secondary coil. So the change in flux of the secondary with time, then multiplied by the number of turns of the secondary, you know that is going to be the EMF of the secondary. So invariably, I can simply say that for mutual inductance, okay, mutual inductance multiplied by the change in the current of the primary with respect to time is equal to the EMF that is actually induced at the secondary. So that's why they call it mutual. The change is taking place at the primary, but the EMF is actually being induced at the secondary. So that's why it's called mutual. So this is actually mutually coupled with this, and the vice versa. I can also go the other way around. Let's say the variation is actually taking place at the secondary. The varying in current is actually taking place at the secondary with respect to time. Then definitely is proportional to the flux linkage of the primary with respect to time. Okay, so of course you know very well that if I should introduce an equal side, I'm gonna have another. Okay, I'm gonna have still mutual inductors. M the Ix all over the T is gonna be equal to N the flux of the primary. Please pardon me. The flux, change in flux of the primary. Change in flux of the primary with respect to time. Okay, and the flux of the primary with respect to time. So invariably now I can applying Faraday's law. Okay, we know that this is actually equal to the EMF induced at the primary. So this is gonna be equal to the EMF induced at the primary. So this is called mutual inductance. Why? Because the change in current of the secondary with respect to time actually causes EMF to be induced at the primary. So it's vice versa. If it is happening at the secondary, then the EMF will be induced at the primary. If it is actually happening at the primary, if the change is taking place at the primary, then the EMF will be induced at the secondary. So I hope that is well understood. Okay. Now this is one type of inductors. This is called mutual inductors. So we're going to look at self-inductors. Okay? Self-inductors. Okay, so as the name imply, self-inductance actually occurs when the EMF is actually induced in a coil due to the change in current, okay, with respect to time that is actually happening in that same coil. So when the a coil, when the current of a coil actually varies, then definitely that EMF will be induced in that coil. So in self-inductance, we are just looking at a single coil, of course, which we call inductor. So we are looking at a single coil. Please pardon me. So let's say this coil is being supplied with a change in current. So definitely when the current of the coil changes with respect to time, then EMF will be generated or flux will be induced in that particular coil. Which is proportional to the current that is changing. So that's gonna be um, N the flux with respect to the T. So in this case now, we are looking at just a coil. There's no mutual, just a single coil. So of course, if I replace this by an equal to, I have to introduce a constant. So this constant, this time around that is L, okay? The constant is L, which is equal to N the flux with respect to time. And you know very well that this actually is equal to the EMF. So the L here is what is known as self-inductance. The L is self-inductance, okay? So this is the EMF. This is actually the process by which EMF is induced in a coil due to the change of current with respect to time in that same coil, right? So that is why it is called self-inductance. Okay, so now the SI unit of inductance, either self-inductance or mutual inductance, is actually Henry. It's Henry. So that is why anytime you see a coil is actually being measured by its inductance. Okay, a coil is measured by its inductance of a coil, which of course has SI units of Henry. So this actually brings us to a device known as a coil. A coil is actually a device. Now, what does a coil do? Okay, a coil is actually a device or an inductor. You see, I don't call it a coil, you call it an inductor. That's where the name originates, inductor. Inductor is a device that stores energy in a magnetic field. Okay, it stores energy in a magnetic field. Why? Because as you can see, when the flux linking the coil actually changes, what happens? It produces EMF. So invariably, we can actually conclude that an inductor stores energy, okay, in a magnetic field, right? So now the inductor is actually measured by its inductance, whose SI unit is actually Henry. Now this inductor can actually be connected in series, or it can be connected in parallel to get more inductance. Okay, inductors in series. So that simply means that if I need more inductance, if I want to get more inductance, I can connect inductance in series. So I have two inductors connected in series. So let's say the first inductor has inductance L1, the second has inductance L2, and the third has inductance L3. Okay, so the total inductance, if they're connected in series, is going to be equal to L1 plus L2, then plus L3. So please take note of that. Okay, so if I have 2 Henry, 2 microhenry here, I have 2 microhenry here, I have another 2 microhenry here. So if I'm to get the total inductance, definitely that's going to be equal to 2 plus 2 plus 2, which of course is 6 microhenry. All right, so, and of course, if this inductors is connected in parallel, inductors in parallel. Okay, so of course, this is parallel connection. Pardon me. Okay, just pardon me. I have L1, L2, and L3. So, of course, their total inductance is going to be in form of reciprocal. So, 1 over LT is going to be equal to 1 all over L1 plus 1 all over L2, then plus 1 all over L3. Okay, so let's say I have each one of them being 2 millihenry. Okay, so their total inductance 1 all over their total inductance is going to be equal to 1 all over 2 plus 1 all over 2 plus 1 all over 2. So 1 all over LT is going to be equal to, the LCM is 2. 2 divided by 2 is 1. 1 times 1 is 1. 2 divided by 2 is 1. 1 times 1 is 1. 2 divided by 2 is 1. 1 times 1 is 1. So I'm having 1 all over LT to be equal to 3 all over 2. So which simply means that if I want to get LT now, I have to reverse the right hand side, which of course is going to be 2 all over 3. Okay, so 2 all over 3. So invariably, if I want to reduce the total inductance, okay, if I want a lesser inductance, I'll connect it in parallel. But if I want more inductance, I'll connect it in series, because if I connect it in series, the inductance will increase, okay? But if I connect inductance in parallel, definitely the total inductance I'm going to get will be less than the individual inductance. Okay, so I will actually, we are going to solve questions on all these formula theories and of course principles, okay? And we are going to be doing that in the next video. Okay, so see you in the next video. Thank you very much.